Well, hello everyone. Welcome to this Wind Power Engineering and Development webinar, Networking the Wind Farm, a closer look at the equipment that ensures production uptime. I'm your host, Paul Dvorak, editor of Wind Power Engineering and Development magazine. Thank you for joining us. And at this time, I'd like to acknowledge and thank Redline Controls for sponsoring this webcast. Now, just a brief agenda before I introduce our speaker. This webinar will be available at windpowerengineering.com. And a link to it and the slides will be emailed to everyone who is registered. At the end of the presentation, we'll have a brief question and answer session. Now, of course, not everyone that wanted to attend today's webinar could be here, but you can help them learn from it by tweeting the key takeaways and key points that you think important. And your tweets, be sure to include the hashtag WindWebinar. Now, after the presentation, I'll read the questions that you and the audience have submitted. You can do that by typing them into the questions box on your GoToMeeting panel that should be to the right of your screen. If it's not, look for a small red arrow and pick on that, and the question box will appear. I'd suggest not waiting till the end of the presentation. Type your questions in as they come to you, and we'll try to answer as many as possible before the time is up. Now let me tell you about our speaker, Barry Turner. He is a Network Engineering Manager for Redline's Industrial Networking and Automation Products. With more than 15 years of product, sales engineering, and network administration experience, Barry has extensive network and communications knowledge in industries that include wind, solar, and other renewable energies. Redline provides industrial products that enable companies worldwide to gain real-time data visibility that drives productivity. As a result of the company's Entron and SixNet acquisitions, Redline now offers a comprehensive portfolio of industrial Ethernet switches, cellular devices, and automation products that connect, monitor, and control. And with that, let us begin. Barry, the microphone is yours.
Thank you. Thanks. Appreciate you guys having me here. And I'm just going to take about roughly about an hour of your time, and we're going to talk about Ethernet and how that correlates and how we can use it in our wind turbines to provide a reliable network just for control and monitoring of the equipment you use. So we'll go ahead and forward on into this. And so today what we're going to talk about is networking the wind farm, what it takes to get a network up and going, and we're going to go inside the wind turbine itself and look at some of the components. The networking switches, a little bit at HMIs and how we can use those to get diagnostic data about the network and other devices inside the turbine. And then we're also going to see what we can look at about ensuring uptime. So we're going to look at building a resilient network so that, that if there is any kind of fault anywhere, fiber outage, cable, anything like that might break or component failure, we have something that keeps it up and going. So Ring is what's going to do that, and we're going to show you how that works and how easy it is to set up. And as far as scalability goes, you know, the switches have to, you know, allow that, and ours too. So select the right media type. So we're going to talk about fiber optics because that is used a lot in this type of network. There's a lot of distance between all of these turbines, and so we need to get fiber optics is what we use to make sure that we can get the distance we need out of that. Copper has some limitations, and we'll talk about those. And then wireless. So we talked a little bit about Redline buying Entron and SixNet, and they did that because we have some fantastic switch lines, some amazing, reliable switches. But we have two companies, and both companies have a great portfolio of products, but each one has or had a few gaps in there to meet the needs of the customer. And so now when the two companies combine together, or now three companies, now we have a complete line, you know, to the breadth of product. So you get the best of breed to choose from, and wireless is one of those things that we get to add on the cellular side. And we're going to show you how to set up alerts with the HMI so that you can proactively find where faults might occur, anything that might happen, and have that email you or send you a text message. And then, like I said, proactively troubleshoot the network using the HMI. So we can look at diagnostic data in the HMI and pull data out. So and we'll go ahead and move forward. So with Ethernet is what we're going to talk about today. Ethernet's been around for a long time, about 40 years, roughly 40 years. And it has evolved a little bit, but for the most part, it stayed intact. The reason it stayed intact is because it was a good plan to begin with. And things have been built on top of it to provide more functionality and expand its features, but the underlying principle is relatively the same. because it was, like I said, a great concept. So we're going to look at momentum because Ethernet is everywhere, and some of these places you may not actually realize it is, but it is all over the place. You use it every day, of course, and it's in pretty much every communication or passive communication. And then we're going to look at a few different applications. So, so we'll go ahead and move to the next one. And in 1973 is when Ethernet was first thought about by Bob Metcalfe at the Palo Alto Center in California. And he came up with he needed a network that would allow multiple devices to connect to one medium and have access to other resources on that. And you know, today or in the past, you used serial type communication, which works fantastic, but it has limitations too. So serial communication has, you know, you have to daisy chain it if you're going to want to extend that out. And then we have distance limitations, we have bandwidth limitations. So going to Ethernet is a very good idea because now we're able to get away from all the limitations that serial has. And plus, when you're using serial, you're kind of tied to a vendor. So you pay a premium for a part that connects serial that talks to a particular protocol. But you can use Ethernet and you don't have to pay that premium like you did in the past. So that's the reason why people buy Ethernet switches or want to move to Ethernet switches. Most all of the equipment that you're buying today has the Ethernet port on it. And the reason is because they want ubiquity, and that's what Ethernet gives you. So Bob Metcalfe created the Ethernet based off of the Aloha network. And Aloha network was a network that allowed connection from all these different islands in Hawaii, and it was wireless communication. And so instead of having to get on a ferry to go from island to island to use a centralized computer, they wanted to use a wireless network to do that, and that's what the Aloha network did. The problem is that network was very inefficient. So you can see right here, it's about 18% efficient, so there's a lot of overhead and a lot of waste. So Ethernet fixes that, and it uses this protocol here, which is CSMA/DD. And so what that means is carrier sense. It's able to listen on the line to see if someone else is talking. Because if you have one medium, only one person can talk on that medium at one time. And that's what that does. Multiple access means we can have multiple devices connected to the same medium. And in collision detection, if two people talk at the same time, we have to figure out what to do to make sure that it's rectified. So it's just like talking with somebody on the phone. If both of you talk at the same time, there's a good probability that either one of you understand what you were saying. So, and Ethernet can be highly effective, or efficient, I'm sorry. And it is today. Actually, today we don't use CSMACD as much because we have full duplex communication. This is where the momentum comes in. And you look at 1970s, 1980s, 1990s, 2000, 2010. So roughly 40 years ago is when Ethernet first came out. You can see that the patent was filed by Xerox in 1975 based off Bob Metcalfe's, and just a little trivia if you guys are into that, Bob Metcalfe later went on to form 3Com, and 3Com is a company that he ran for quite a while, very successful. And they got their start in making Ethernet adapters. And you can see in the 80s, 3Com ships their first adapter in 81. And in 1985, 3Com sells, 100,000 adapters all, worldwide. So that's a big jump. And the reason that people jumped on that is because it was ubiquity. You can use this card, but you can put it on these different devices, and it works relatively the same way. You can put it in a printer, you can put it in a PC, instead of having to pay a premium every time. And then in the 1990s, this kind of baffles my mind when I think about it, is that the internet is really roughly 20 years old. So it's 20 years old, but it's something that I check every single day. Every single day I'm on the internet, and I think that the majority of people are on the internet every single day. But 20 years ago, it didn't exist, or not in the form it is today. But we knew nothing about it, but now we use it. So you think about the exponential growth of technology as a whole, as we move forward, the ramp just goes up sharper and sharper. So, who knows where we're going to be in the next 20 years. So, and then in the 2000s, Ethernet IP was introduced by Rockwell, and then it was later, shipped over or handed over to the ODVA, and ODVA actually takes over ownership of that, and they actually manage it now. So, in 2003, we started looking at or having the ability to do 10 gig, and I added this Verizon Metro Ethernet out there, and it's really not important for what we're talking about today, other than the fact that it is an end-to-end solution now. So the technology used to be Ethernet was plugged into the back of your PC or your servers or your end devices, but once you got on the internet somewhere, you cross over a different protocol and use something different. Metro E uses Ethernet, and so your Ethernet from start to finish. And Metro Ethernet is growing fast because it's easy and it just does what it's supposed to. So 2010, Ethernet is everywhere. That's absolutely true. So I don't know if you guys keep up with these magazines here, but these two magazines had an article in them, and I thought it was very interesting. They called the Internet of Things. And in the article, they talk about how everything's going to be connected and everything's going to be smart. And right now we have our smartphones, and then we call them smartphones because they are able to anticipate what we need, what we want, or do a very good job of that. And they want to do that with objects. So just, things that are out there. Ethernet is going to be the protocol that they use to communicate, or some form of it. So Ethernet is going to be everywhere, and it continues to grow and expand. And the Internet of Things is just that. It's having the ability to move from one location to another location and using my phone to know where I'm going and what I'm doing. And the Internet or program will actually anticipate what my needs may be. So as you leave work, you cut off your computer and leave work to go home, you might send a text message to your wife saying that you just left work. Well, it happens automatically because of the program that's in the background. Just like that, you might get home instead of having to match your your alarm or your remote for your garage door. It makes sense that it's your car coming in. You don't have to smash anything. It just opens as you pull up. So lots of things that are like that. Technology just keeps growing and growing and getting to be a bigger part of our life, which excites me because that's what I do. But the Internet of Things is growing, and it's a very exciting time for anybody in technology, and it's where everything is going to be at. So we look at a couple of different things, a few different applications here. So a lot of the TVs that we buy today, especially all the smart TVs, have an Ethernet jack on the back. It's either an Ethernet jack on the back, or we have a wireless card that's inside the TV, but we have that in our TV. If you look back 10 years ago, we would have never actually anticipated. I would have never thought that I would have had an Ethernet jack on my TV. At home, I actually don't have cable and I don't have satellite. I have an Apple TV, and I stream all my media, and that's the way I do my entertainment. And that is kind of the way that people are going as we move forward. People are using their cell phones now instead of using the landline, because technology is taking over. And Ethernet is at the core of that. So you look at businesses, consumers, you got home automation, which is a growing market. You got process control type stuff in manufacturing. We're able to build stuff quicker, cheaper, and better using machines and Ethernet as a communication. And so you look at media. Streaming media, we need more bandwidth for that kind of stuff. And of course, wind turbines. So Ethernet is definitely here. These are actually, autonomous systems that are producing energy using the wind. So they take kinetic energy and they produce that. So how are we going to bill for that? We have to be able to monitor that. We have to know that it's working all the time, and we have to meter it. And so that's what Ethernet allows you to do, is take that data that you're pulling out with whatever sensors or control devices you have in this turbine, and then send that data somewhere else to be collected and manipulated so that it makes sense to you and so that you know what you're actually producing. So you know what you're billing, and you get trend analysis, all kinds of data using Ethernet. But you couldn't get that before. If you just stuck these guys out there and let them run, of course, they wouldn't run. Even if we knew how to build turbines that work the way that they do today, without some type of control, they would end up, self-destructing. They have to know where the wind is coming from. They have to know how fast they're going, and all that stuff has to happen inside the turbine itself, and that data ends up being transmitted on Ethernet at the back. So, one of the things that's happening right now is retrofitting these wind turbines. There's tons of turbines throughout the world, and it's time to retrofit them. And why is it time to retrofit them? Because they're not near as efficient as they once were. We have new ways of doing things. We have new devices that we can put in there that will do what we need it to. And so we can increase the efficiency, we can increase monitoring capabilities, and we can increase our control or enhance our control so that we have better, more granular control over what's going on out there. Now we have redundancy that we can put out there. Lots of stuff we didn't have 20 years ago. So like I said, you look at the exponential growth of technology as a whole, and that any technology you look at has had exponential growth throughout. So we want to make sure that we want to drive efficiency. So we're going to add more sensors, and we're going to have more data points. We got better control, deeper monitoring capabilities. So if we go up inside the turbine here, if we look at these devices, this turbine may be has been up here for 20 years, but the controls in it are relatively new, except for if they've been retrofitted. But if it's a very efficient turbine, the controls are new. They have better functionality out of it. So that's the reason why people are retrofitting these, is to increase the capacity and increase the performance in these turbines so that you can put better controls in it, better monitoring capabilities in it, so that turbine as an investment is producing more money for you. And then now we can increase productivity by allowing you to do remote monitoring. So in the past, how would we get data out of this turbine? Well, very few ways to do that. Wireless has always been around. Cellular has been around for quite a while, and but the amount of data that we can actually pull from that has been not quite as much as what we need. So now with wireless getting up there where it needs to be, with LTE coming into play, and with 802.11n coming into play, now we have enough bandwidth to actually produce the data that we need to collect. And so we get more visibility in our network because we can look deeper. We get quicker response times when something goes wrong because we have alerting features. And since these devices, or since these turbines are all connected to one another, but they may not be connected to the internet directly, we can allow, like a cellular router sitting out on one of the turbines that actually communicates everything back. And so, and then we enhance preventative maintenance. So we can schedule, work to be done at a certain time. We can look at, what's going on, what the trend is, what the performance is of that particular turbine, and make sure we get somebody out there to actually do whatever maintenance needs to take place. And instead of having to send somebody to the turbine, just to guess. So it allows us to become proactive instead of reactive, which is what everybody likes. Looks better and works better. So enhanced control. So we increase, or we can get better braking now, which means that we're going to extend the life of the turbine. A lot of these turbines that had some issues that may have not worked out the way that the installer had hoped. A lot of that is because the braking didn't work exactly like it should. The control mechanism didn't work just like it should. So as we retrofit these turbines, we're able to put better controls and better devices out there to do that. And like I said, all the devices that you're buying now have an Ethernet interface on it. So and more efficient pitch control. So that means that we can control it better, and we just make sure that it's turned to the wind properly, and all that data gets on the network somewhere. So everything, what I did in my past life before I started working with Red Lion, and I've been here for about 2 years, was network administration. And network administration, you have data that transfers from a client to a server, or to the internet to a server, or back and forth. But I didn't realize how deep internet or Ethernet is involved in communication with essentially everything. So, traffic light controls, for example, way stations, toll bridges, everything has Ethernet at the backbone, including these Ethernet, these turbines here, which have Ethernet on the background or backbone. More control, you got more power out of that, and that's why we're retrofitting these towers. So what about remote access? Like I said before, now that we have Wi-Fi and we have cellular, now we can connect in remotely into these guys and pull the data out. What if we think something's going wrong, or we're not producing the amount of power that we should out of a particular turbine? We're able to connect into that remotely without having to send a technician all the way out there, and we can do diagnostic work on what the tower's doing. So we can figure out, why it's not performing like it should, without having, the cost of sending somebody out there and having to send them all the way up to the tower to take a look at it. And, it could be just a software change. So, and then, in the past, people had connections with like a T1 line or ISDN or something like that, and those lines end up costing a pretty good bit of money. But now with cellular, with Wi-Fi communication, we can allow Wi-Fi to cost you nothing as a monthly fee. You pay for the radio itself at the very beginning, And then the Wi-Fi communication is unlicensed, so you use what you need to. Cellular, you pay for a machine-to-machine cellular connection, and you pay a very low amount for the amount of data that you're actually pulling down. And so it's, cost comparison, cellular is much better than a T1 connection would ever be. And then, like I said, reduce the need for on-site visits, because now we're able to proactively see what's going on in the network without having to get out there and get into the turbine and go all the way up to manually inspect what's happening. So quick response time, of course, that enables that because you don't have to go out there. And then enables predictive maintenance, of course. And then let's see. So let's go inside the turbine right quick. So fiber between towers, and this is what just a typical turbine or wind farm is going to look like. You're going to have a wind turbine scattered throughout at the optimum elevation for the environment there. And we're going to have a turbine here, but there's going to be a long distance between each one of the turbines. And the only way to get there, because copper has a limitation of 328 feet, the only way to get there is fiber optic cables. So we're going to use fiber optic cables to go between the turbines, and we may use copper inside the turbine itself as long as we can get there. And so this shows you just that. It shows an Ethernet switch, and there's a ring, and the ring that allows us redundant connection between each one of the towers. And so, and the ring connects all together. And with in-ring, which is our proprietary protocol that allows fast heal time you're looking at about 30 milliseconds. With the standard for IT ring protocol, which is RSTP, your heal time is about 1 to 3 seconds. Well, the problem with that, 1 to 3 seconds, a lot of things can happen, and we need it to happen immediately, and we need to know that these PLCs and these drives are communicating, and there's a scan time in it. We want to make sure that that scan time doesn't, we don't miss that scan time. And so we need a very fast heal time on our ring, and that's what in-ring offers. And then the ring ensures uptime, because like I said, if you were to have an equipment failure or a fiber optic failure, say that someone cut the fiber in one spot, the ring itself would be healed in 30 milliseconds, which is very fast. And so your PLCs would communicate. If you had peer-to-peer communication between your PLCs, between your towers, they would never know that there was an outage anywhere in the network. And HMIs allow you to monitor the network at in the nacelle from the base, so you don't have to go all the way up there to see exactly what the devices up top are doing. So this is our G3 HMI, and if you guys have ever used it, it's fantastic. HMI has Crypts on the back end, which is software that allows you to easily program the HMI and pull the data out. And that's a 708FX2, which is just an Ethernet switch that we have, which is kind of our sweet spot for our Ethernet switches if you don't need a modular Ethernet switch. But the same thing holds true about both of those products as far as ease of use. So most of those you can pull out of the box and have them up and going very quickly. And that's one of the things that we're going to talk about or look at whenever I show you how to set up in-ring and exactly how easy it is. If you look at doing a ring, it seems like it might be complicated. Well, with the software engineers have made it so that it's not for these particular switches. So, so I mentioned earlier we have a limitation of 328 feet for copper. And since we have that limitation, we can't go above that. What if you have a 400-foot tower out there and we need to go past that? What will we do? Well, you put an Ethernet switch in the middle, and that Ethernet switch is going to act as a repeater to the same exact thing. It's going to pull the data in, and then you have another reset of 328 feet on top of that. If you have a tower that you can't get there, you can't put anything in the middle, then fiber optics will be what you want to use to get all the way to the top. And so we have 100 meters is our maximum for Cat 5, Cat 5e. That's Cat 6A also. And we're going to talk a little bit more about the media types in just a little bit. So if you look inside the turbine, it might look something like this. And this is just a diagram that we have on some white papers, and you guys have maybe seen it before. But if you look at the shock and vibration specs on our Ethernet switch, it is very high. And it's really high, especially compared to our competition. The reason it's so high is because we've been in wind for quite a while, and we know what happens. We know what needs to happen, and we know that Ethernet switch might have to be in that hub. And so if it's in there, helping control the pitch of those blades, then or passing the data that controls the pitch of those blades, then it needs to have high shock and vibration spec, and which all of our switches do. And so that's what we're showing here, is that when you're putting in a network, you got to make sure that the product that you're putting in there meet the specs for the environment. And so I do like, I teach an Ethernet class where we talk about Ethernet 101 and what it's used for and how it works. And one of the things that I talk about is if everybody has Ethernet at home, and so you have a Linksys router at home that you get access to the internet, and when your daughter complains that she can't get access to the internet, what do? Well, you go downstairs and you find the hub or the switch that you just bought, and you power it off, you power it back on, and within a few minutes she's back up and going, and everybody's good. But in a situation like this, you don't have that luxury. You can't reboot these things. They have to be running all the time. So you need a hardened switch. You need a very reliable switch. So and you want a switch that you can put in place, and it's very easy to configure, and it just runs, and that's exactly what we have. So extreme temperatures, again, we have to match the product for the environment that's going to be in, and these things can be all over the place. And they could be in the nacelle where it's very, very hot because of all the power being produced up there, but it could be in the base where it's very cold. It could be, almost anywhere. And these towers can be anywhere. So you look at scorching heat, the Arctic cold, humidity. There's all these things, these factors that you have to pay attention to when you're putting your equipment in here. And so if you put a consumer type switch or device in there, you're going to see failures. And if you see failures, then you're not going to be pulling, you're not going to be able to control your tower like you need to. You're not going to be able to pull the data out that you need to. And it's just a bad idea. So the first column on this particular slide is where I spent most of my life doing network. And so there was always a closet that all the data was housed in, or the data equipment was housed in, but it was always air conditioned, and then we had a filter in there, so there wasn't a whole lot of dust, and the equipment was taken care of. The problem is that there will be a lot of dust. There will be a lot of environmental properties that you can't isolate this equipment from, without putting it in some type of a box. So you want a very hardened device, and that's what we have now. So you're looking at negative 40 to 85 C, and then you look at shock and vibration, 50 to 200 Gs, and we've got over voltage protection at each one of the ports. So you got 16 kV diodes at each one of the ports on your Ethernet interface, and then mean time between failure. And that's huge. And you see that the typical commercial switch is about 25,000 hours. And that's it. That's not a long time, right? And part of the reason why that it's like that is because it has a fan on the inside of it that runs, and that fan has a bearing in it, and those do go bad. So if you have a switch that has no moving parts, it's less likely to go bad, and ours don't have a fan in it, and that's the reason why. So building and deploying a resilient network and a scalable network, we're going to select the right media type, and we're going to use wireless to remotely monitor the performance and proactively troubleshoot the network using HMI. And so we're going to be able to take a look at what the HMI is going to tell us about what's going on in the network quickly and easily, and just a few points we're going to touch on. If you see this, this is bad. If you see this, this is good, that kind of stuff. And then wireless or remote, the performance. So like I said before, we're just going to talk about how we could use wireless and cellular in combination with one another to actually provide a solution without having to run fiber optic cables between each one of these towers. Now, wireless is, you're not ever going to get the same speeds that you are potentially able to get using wired connections, but a lot of times running a fiber optic cable or putting something in the ground is cost prohibitive, and wireless is a better solution. So selecting the right media type, we're just going to talk about like I said before, the different kind of cables, the connectors, and why a Cat5 cable is different than any other cable that has, copper conductors in it. If you're an electrician, a conductor is a conductor. However, network engineering, there's a lot of things you have to pay attention to. There's this media is twisted to make sure that the signal gets where it should get to. This could be a network, and you see that you got ring A, ring B, ring C, ring D. And we have these rings out here. And if we were to lose any one of these Ethernet switches for whatever reason, power outage, which happens a lot, and any kind of network, the power is the point of failure most often. And so we have redundant inputs on the power supply on all of our Ethernet switches, so you could have multiple power supplies, or you can have a power supply and a battery backup, however you felt most comfortable doing it. But if so you were to have a power outage at right here, say the switch at the very top. If you were to have that switch fail for a power outage or whatever it may be, the rest of the network is still up and going. So if this was a path that the data was flowing before, and that switch were to go offline, or we were to lose a fiber optic connection, we need something that's going to heal up very quickly, and that's what in-ring does. Like I said, in-ring heals in about 30 milliseconds. And so if we had peer communication in our PLCs here to here, or wherever, let's say maybe this guy down here, we have 30 milliseconds between this whole network. And the way we do that is we have these these four rings here, and we're connecting these three rings to the main ring using a protocol, or another proprietary protocol called InLink. And InLink allows that same heal time we have with in-ring, just we have these four switches that allow us to do that. And so that we have a primary and a standby link. And if we were to lose the primary, we'd switch over to the standby link in 30 milliseconds. So it's very critical, because we want to make sure that we are always getting the data that we need out of these turbines, and that we're always able to communicate with the turbine. You know, if you were to lose communication completely to a turbine, how long would it take, or how long would it take you to get out there, and how stressed would you be before you got out there to figure out what's going on? I mean, think about all the things that could go wrong with the turbine just running itself without any monitoring. So you need something that heals very quickly, and again, you got metering. You need to make sure that the power that you're producing, you're able to bill for it. Quick little video that I'll show you on how easy it is to set up in-ring. And in-ring is just that protocol. And normally, when you're setting up a ring on a network, you have to set up a lot of stuff. You have to do a lot of things. You have to jump through hoops. You have to make sure you tell it which one is this and what's that and how it's going to connect. With the Intron switches, the Intron switch line, the only thing you have to do is set the ports the way that they should, which means plugging them in the right ports, port 1 and port 2, carry on the ring. It's either the first 2 ports or the last 2 ports, and then log into one of the switches and make a change from auto member to master. You don't have to log into every switch. You only have to log into one. And so in this demo, what I'm actually going to do is I'm going to log into one of the switches, because all the switches have a default IP address of it on them. And I'm going to log into one switch, change the IP address to something unique so that I can log back into it, just so I can show you what it's doing. And I've got, what is this, 2 ports. These switches that are around the ring, and when one fails, the other one will pick up, and the heal time is 30 milliseconds. So what you'll see is I'll add an IP address, and then I'll reboot the switch, bring it back up, log back into the same switch, and then I'll take and enable in-ring. I'll save and reset, and once I save and reset, you'll see that the in-ring is up. Now, when I did this video, and I did the video because if you have multiple connections to 2 different networks, you could have problems. And so I did a video beforehand, and so whenever I try to connect to the switch at the very beginning, you'll see that its page can't be displayed. The reason it can't be displayed is because I'm not connected to the internet. I'm just connected to these switches that I was configuring. So we'll go ahead and click play on the video. And so the ring manager is the switch that I'm logging into, that 708TX at the very top. I'm logging into that guy and just making a couple of changes. One is going to be the IP address, and the other is going to be the setting up the ring itself. So this is the ring manager. You have one switch on the ring that is a manager, and it's taking care of the ring throughout. This is where I'm pulling up Internet Explorer. I'm just logging into the default IP address of the switch. I'm sorry, I know you guys can't see the IP address I'm typing in there, but it's the default. I'm just logging in with the default using the password of the switch. And the first thing we do is administration, and then system, and then modify. And the default IP address will get changed from 201 in the last octet to 203. I'm going to save it and reset. So just save the settings, and then does a power cycle. Once it comes back up, I'm going to log back into it. The switch will actually, the software in the switch is actually going to forward me to the new IP address, which is 192.168.1.203. And it's going to reset that switch, and then it's going to forward me to it so I can log back in, and I'll make a change for in-ring. Take the switch just a second. I'm logging back in now. I'm logging back in. I'm going to go down here to in-ring, change configure, mode, modify, And auto member, all the switches shipped as auto members. I'm just going to change that to manager, I'm sorry. And then you select which ports. Like I said, it can be the first two ports or the last two ports. And I'm using TX1 and TX2. I'm going to disable RSTP, which is the default. Save and reset. And as soon as the switch comes back up, it's going to tell all the other switches that it is now the ring manager and that a ring is formed. And so they kind of fall in line and do what they're supposed to in the path the health packets around in the ring so that we're able to give you a 30 millisecond hail time. And there's a lot of different indicators on the ring. So if a ring were to fail, if you're using the industry standard that I talked about before, with rapid spanish, there would be no way to tell where the ring failed. You would just, or the redundant connection failed. You just know that you might have had a broadcast on. So now we see the green line at the top, in-ring is okay. I know you can't read that, but then this is on the in-ring manager, shows us that the ring is okay. And if we were to have an outage at any point, then it would have to turn red. And this page shows us that we have this many switches in our ring. Only had 6 switches there, but shows the IP address of the ring manager, which is the 203. The rest of them are the default IP address. I mean, I didn't change them. I didn't log into them. Everything is factory default. So this is how much time it takes to set up an in-ring, which is very little. And I can use, we have a software called InView. You can use InView to monitor the switches. So without putting an IP address on them at all, you can actually figure out exactly what's going on your network. And that InView data that gets produced from our switches is actually what we end up collecting and using in the HMI to see what's going on. So, and that is about it on the in-ring. But you can see it's very, very easy to do. And so part of the success that we've had with the Intron line is that the switches are very easy to use, but they have advanced features. So if you don't need them, you don't have to have them. So most of the guys that are using our equipment, they're not network engineers, and they really don't want to be network engineers, but they do know a lot about the applications that they use. But they have learned that Ethernet seems to be the backbone of the data, so they have to know something about it. Well, with an Intron switch, we give you kind of the same experience that Apple used to give in years past. Just put something in your hand that you can use, and it just works, and that's what this does. So it just works, very easy. So using the in-ring technology, so the ring manager sends a health packet around the ring to make sure that it's intact. Once it fails, it does a repeat attempt a couple of times, and then at 30 milliseconds, it will heal. So if it's broken. And so you get reporting features with this that you don't get with RSTP, that you don't get with a lot of ring protocols. Like I said, if a failure were to occur, it would just occur, and you would have no way of knowing exactly where it is. You'd have to go hunt down the loss. So if somebody cut a fiber optic connection somewhere because they were, laying a line down or something like that and cut your fiber down, you might not know where it is without logging in each one of the switches and see which port's down. With in-ring, we're going to tell you exactly which switch it is and which port on that switch has seen the failure. So it automatically heals, and if the ring breaks for whatever reason, it's just a daisy chain like you were before. So you want to fix it as quickly as possible, but you're still up and going for the foreseeable future. I need to hurry up just a little bit, but 802.3 is the standard for Ethernet, and Ethernet is, like I said, it's the base, it's the core protocol that everything else is stacked on top of. And when it was first invented or created, it was 10 megabits per second to use it. But the distance that we could go was 100 meters or 328 feet. That IEEE is the guys that actually manage that and maintain that. It was ratified to 802.3U, and we increased the speed. We increased the speed by changing the clocking mechanism, and we're able to get more bandwidth out of it. So now we're looking at 100 base T or TX or FX. So the FX stands for fiber, the T stands for twisted pair, and the MM that you see in this column right here is multi-mode, and then the SM is single mode. And we have 2 different types of fiber, single mode and multi-mode, and both of them have different properties. So the multi-mode is going to be what we use for a shorter distance, so up to 2 kilometers. And then the single mode is anything past 2 kilometers all the way up to 80 kilometers. And so it's the fiber optic has different properties in, as far as how thick it is and what kind of light we're using to produce, or what we're using as a light source, and that's what determines the distance we're able to get out of it. It's verified yet again, so you look at 802.3Z, and we have 1,000 base T, or a gig, and that's what people are using the gigabit today. Now, this a gig connection is not what we always need. Most of the data on your network, 100 base speed is fine. So 100 meg switch is what a lot of people usually get for this type of application because we're not sending a lot of data. We're just sending a lot of packets per second, but we're not sending really big packets. So we don't need a huge pipe. We don't need to pay a premium for gigabit Ethernet at every one of the ports because we're not producing a gig of traffic. And so you buy a 100 meg switch with maybe a gig backbone. And so your ring may be a gig, but the ports, the individual ports themselves that connect to the end devices will be 100 meg. So again, we didn't really change the distance on the copper. We can still only go 328 feet or 100 meters. But with the SX and LX, it would be short haul or long haul. So that SX would be multi-mode. And you can go up to 550 meters. If we went with the long haul or the single mode fiber, then we would look at going 10 kilometers to 70 kilometers. And I think that's about all that we need to talk about on that particular slide. And then the next one, we're talking about Ethernet copper. So it started with Cat 1, and most all of the, well, the twisted pair did come from the telephone side of the thing. So the telephone has been using twisted pair for quite a while because of the way that they need to send data. They've been around a lot longer. But we've adopted the way that they use twisted pair so we can make sure that the signal continues on its distance that it needs to. And so we look at Cat 5, Cat 5e, and Cat 6a. Those are the ones that are used primarily today. We get asked a lot of times because most of your IT data guys are going to be using Cat 6a, which is kind of the newer stuff. And they want to dictate what you put out there. You may be talking to someone that's actually going to do install of your copper, and he says you need Cat 6a. There's a little bit of a premium for Cat 6a over Cat 5e, but there's really not a need for it. Cat 6a, the only advantage that you get over Cat 6a that you don't have with Cat 5e is the fact that you can do 10 gig. And you can only go up to a gig with Cat 5e. With Cat 6a, you can go up to 10 gig. Like I said, we're not needing a whole lot of bandwidth on most of these, or the majority of these applications. We just need a lot of packets per second to be able to process. And so Cat 5e will work in most all applications. If somebody pushes and says, okay, we're going to put Cat 6a in, that's fine. It will still work just the same. Just know that the cable itself and actually punching the cables down and all that kind of stuff will probably cost a little bit more. Not a lot, but a little bit more. But it's not always needed. So these are what the copper looks like. You got EIA 568A and 568B, and these are just different standards. And really the only difference between these two pictures here, A and B, is the send and receive. So if you look at the green and the orange, they're just twisted, or they're swapped. And so the green and the orange are the send and receive. And so when you're using two devices that are like devices talking to each other, you have to swap the send and receive. And so it's just like a telephone. You got one part you listen to and one part you talk on. And if you're talking to somebody else, they're swapped. They have something up to their ear that you're listening to and something they're talking to on the other side. And so we have to swap the send and receive when we're talking with like devices like that. So if you had two PCs that you were trying to talk with one another, or two switches that you were trying to talk with one another, you would use a crossover cable to do that conversation. So so it would switch the send and receive for you. And so if a crossover cable has just got A on one side and B on the other side, and that's what we used in the past, and it's not that important now because most switches do what's known as auto NVIX, which does that in the switch itself. Most PCs do it too. And so it detects to see if it needs to switch it, and it does it for you. And this other picture here is just showing you the copper in, or the RJ45 connector and the conductors that actually make contact to the conductors in the cable. And this is what fiber optics look like. Of course, you got a couple of different ends there, and we're missing some pictures, but we'll be okay. We've got multi-mode, single mode fiber connectors, and we've got the way the fiber is measured, I guess, or you've got multi-mode is 50 or 62.5/125 micron. That first number is going to tell you exactly how thick the fiber optic cable on the inside is. And so, you think about how thick it is. If you look at the single mode at the bottom, that's 8 to 10. So it's a good big difference between the single mode and the multi-mode and the thickness of the fiber optic cable itself. And so the multi-mode is going to use an LED as a light source. And an LED, of course, is a lot cheaper than a laser, or a lot less expensive. And a laser is going to cost you to produce. And so that's the reason why multi-mode transceiver modules cost a lot less than single-mode transceiver modules. But you get more distance when you're using laser. So if you're going in close proximity, then multi-mode may be what you want to use. But if you're using multi-mode, the fiber has to be multi-mode. The one image that's actually showing here is an SC type connector. And there's just, think about it, it snaps in SC. And ST is kind of looks like a BNC type connector where you push it in, it's got a little spring loaded, and it hugs in. And so a benefit to that is if there's any vibration at all, it's spring loaded and it's actually twisted on there. So if there's vibration, that'll help you. LC is kind of the type in that's the new standard. Most of all of our gigabit switches use an LC, or all of our gigabit switches use an LC type connector, and it takes up a lot less footprint on the front of the switch itself. Now this one right here shows us a wireless and how we can use cellular and Wi-Fi together. This is an application that they have all these turbines all over the area, and it's in the middle of the mountains. And the wind farm was owned by one person, so we want to pull all the data back in to one location. However, you see the distance there. The distance from resident A to turbine 3 is about 7 miles. So that's a good distance there. So you're looking at fiber optic cable is going to cost you a lot of money. So we were able to do the analysis and do the link budget calculations to tell them what kind of equipment you would need to actually go from here, from resident A over to turbine 3 and pass traffic at, at a distance of 7 miles. And so we have to, there's different antennas that we have with our wireless devices, but we can do that. Now, one thing that we can't do, wireless is line of sight, so you have to be able to see where you're going to. So if you look down here at the very bottom, this is a ridge here. And so if we were trying to go from resident A to turbine 6, that would never happen because they didn't have line of sight between each other. So what we would end up doing is either pulling that data back to turbine 3 with another radio, or using cellular to connect that particular turbine back to the network. And so you got a lot of different ways to do that. And usually a mix of the two is the best way to get there. So here's our HMI, the G3. Like I said, it's a very easy to use software, very sticky product. If someone uses the Crimson software, they're pleased with it and they don't really want to move away because it does exactly what it should do. It's easy to use, and we can pull in port statistic data from the InView that's produced on the Intron switches. And so we can monitor our switches in real time. And so we can actually set up alerts. So if something were to power down and the Ethernet interface was not plugged in anymore for whatever reason, or wasn't receiving a signal, then we could alert ourselves with text messaging or email. So, and this video is just, it's the web interface of the G3. So I'm just showing you on the video instead of showing you actually what it looks like, but it's very similar to this. So we got switch 1 and switch 2, and all I'm going to do is I'm just going to click one of the switches, and then I'm going to click one of the ports and show you this data that's being pulled out of the switch itself, and you can't really read that IP address. But it shows you the IP address of the switch, it shows you the model number of the switch, the MAC address of the switch. All this data is being produced and collected by the HMI. And this port 1, and again, you can't read all of these counters here, but these are tons of different counters that the HMI is collecting. And we could set these counters up if we knew what we were wanting to look for example, collisions is something that causes some problems on your network. If you have a half duplex connection, you're going to get collisions. What if you have a duplex mismatch? You would have collisions on that connection, but you may not know that that's happening. So we could set up an alarm to look for those, and then send us a text message if something were to happen. We could do that on too much bandwidth going through or too much being used, broadcast storm, tons of different things that we can alert on using the G3 HMI. We have a DSP, which is a product very similar. So you can pull up a screen that looks just like this with a DSP, and it has the same exact software. You can configure it the exact same way. It just doesn't have a touch screen on it that you can have up there. Now, one of the benefits of the DSP that you guys would be interested in is as you retrofit these towers, you'll be pulling some equipment out and putting new equipment in. So you may have a PLC from one manufacturer talking to a PLC of another manufacturer if that's what you would like to have happen. but these PLC manufacturers may not all have the same protocol installed or work and talking together. The DSP will actually do protocol conversion, so it'll talk from one protocol language to another one for you, so it acts in the middle. So you don't have to just pull everything out of the tower. You can do it, in a phase process instead of doing it all at once. And so what I'm showing you in this video right here is just that we can pull that data out of the switch itself and visualize it on HMI. So you could walk over to the base of the tower, you could have access to the network statistics without having to go all the way up there. You can get network statistics from the G3 without having to be a network administrator. You can have it preset to give you the information you need instead of having to get you a Wireshark capture every time and see what's going on. And so it's quick and easy. So I think we're getting close on time here, but just a couple of takeaways here. So we talked about how to build and deploy redundant networks so that we have plenty of uptime and that we make sure that everything is functioning and communicating. And then we're going to safeguard against failure by putting the right equipment in these turbines. So we'll make sure we put a very hardened, rugged equipment out there, and we don't put commercial or consumer edition type products out there. And monitoring control. It's huge. We want to be able to monitor what's going on in the network. We want to be able to control what's going on. And we at Redline allow you to collect that data, and we can allow you to do some control with it and reduce site visits in real time by allowing remote access. So now that we have cellular and we have Wi-Fi, you don't have to pay or incur all these costly expenses by putting T1 lines and that kind of stuff out there. And then you're proactive. Instead of having to wait for something to happen, you can monitor it as you go, and there's no hidden costs or maintenance expenses that are incurred there. So with that, Paul?
Okay, thank you very much, Barry. And this is a good reminder. I keep thinking wind farms are made of just wind turbines, but there's a lot more to them than that, isn't there? Well, we've got some questions. We've got an inquisitive bunch, so let's get right to those, okay? At the risk of being too repetitive, I'll ask the first one. It's from Clay. He asks, how fast can the Entron's ring heal?
30 milliseconds.
30 milliseconds, right, pretty fast.
30 milliseconds.
Okay. Now, and George asks, even with the fast end ring heal times, is Ethernet still non-deterministic? And you might have to explain non-deterministic.
Okay, so deterministic means that if a device on the other side loses communication, we need to know, immediately what happens. And normally, Ethernet isn't deterministic. If you're sitting at your PC, you're trying to get access to the internet, and you click to go to a website, and you press enter, if the website's not available, there's a timeout. Well, that timeout could take a few seconds before you actually get a page can't be displayed. But in a control type network, you want that to happen immediately. So if the PLC or the drive were to stop communicating with whatever device it was communicating with, you need to know it right away. And so Ethernet, Ethernet IP, for example, was built on top of Ethernet to add that deterministic nature to it. So Ethernet doesn't have it natively, but protocols have been built on top of it that allow that. And Ethernet IP is just one example of many that make that happen. So we have plenty, tons and tons of people. Ethernet IP is the protocol that is used predominantly throughout the United States and a large part in the world. And that's what it does. It gives you a deterministic network. And so it changes the way that traditional TCP/IP works and adds things on top of it to make sure that it communicates successfully. And if a drive were to fail, then the PLC knows right away.
Okay, very good. George asks another question that is on my mind too, is what type of fiber connector do you see the industry standardizing on?
As you go, if you're looking at 100 meg, it's going to be ST. That's what I see for the most part, ST type connector. And ST is probably my favorite because, like I said, it's got that stab and twist, or it's got a BNC type connector. You can push it in and twist it, and it's locked in place. A snap is the SC is a plastic, and it snaps in there. It's still great, but if there's any vibration, it wouldn't be quite as good as an ST would be. Once you move up to a gig, you're looking at an LC type connector, and it's a smaller connector, and it connects to what is known as a SFP module, a small form factor pluggable module, and that's where everything's going that are gigabit.
Okay, very good. Peter asked this question. Are you using multi-mode fiber with ST, SC, or LC connectors?
Yes.
Yes. Okay.
Yeah. We see people use multi-mode on all those different connectors, for sure.
Okay, very good.
The main thing is if you have a short connection, then multimode is going to be what you want to use. And because multimode uses an LED instead of a laser, we want to use that for shorter runs. We want to use a laser type connector or a single mode module when we have a longer distance, so about 2 kilometers.
Okay, I understand that. Okay, George asks, does N-ring facilitate redundant fiber also?
No. It's going to be on one fiber connection, so the ring is just one ring. We don't have a dual ring. But like I said, we have reporting features in it, and we have, alerting systems that we can put in place. Like we talked about the HMI being able to send us alerts if something were to happen. So there's really not that much of a need. And when you do a redundant ring like that, you incur a lot of cost. Now you have more fiber optic cables you have to put in place than you had before. And did we really get anything? Well, not really, because usually those follow the same exact path as the other one did. And so if you have one fiber cut, the other one is probably going to be cut too. So what the better solution is to have one fiber path, in our ring, and then have some reporting or alerting features, and that's what the G3 would allow us to do.
Okay, and Peter asks again, what is the advantage of having a defined ringmaster over a solution where the lowest MAC address becomes the ringmaster automatically?
Well, we're able to say where the ring is. Like RSTP, for example, which is kind of the IT data world's redundancy protocol. It selects the root bridge, which is equivalent to the ringmaster. It's selected by the lowest MAC address. Well, the problem with that is the lowest MAC address is the oldest switch that you bought, because as the manufacturer builds new switches, that MAC address increments up. So your oldest switch will be your ringmaster always. Well, you normally want your fastest switch on the network, the most successful switch on the network, to be the master. So if you let the MAC address just decide which one it is, like I said, you would have probably the least efficiency that you could possibly get.
Okay, very good. That's all the questions, and we've completed an hour. So we're running out of time, ladies and gentlemen. Once again, this webcast will be available for reviewing at windpowerengineering.com. And we also invite you to visit redlion.net/together to learn more about Redline controls. And lastly, you can follow Wind Power Engineering on Facebook, Twitter, and LinkedIn. This concludes our presentation. I'd like to thank everyone for their attention. And from the staff here at Wind Power Engineering Development, we wish you a good and productive day.
Thanks. Appreciate it.